All right, here's this next section. It's called logarithmic differentiation. This is 5.6. In your workbook, so this ends up being a technique that we're going to use. And this stems from the fact that we had your logarithm laws. And your logarithm laws from Math 30-1 were that if you have the logarithm of m times n, this ends up being equal to the logarithm of m, the logarithm of n, as long as, well, and that they have to be the same base. So whatever our base ends up being, let's call it b. And so that was your first one. The second one, which is really pretty much the same as the first one, says if you have the logarithm of quotient, then this ends up being the logarithm of a difference. And then the third one was our power law, and it says the logarithm of m to the n is as an exponent ends up being n times the logarithm of m. And that just ends up being a consequence really of the first rule. So what this is doing, what these are doing, is it's taking multiplication and expressing it instead as addition, or it's taking an exponent and expressing it instead as multiplication, which kind of means that we're making the operation simpler, which is what mathematician John Napier was trying to do when he came up with logarithms. Is he was trying to make it simpler calculation-wise. And that's kind of our approach of what we're going to do with this, is we're going to find that if you've got a product of things, we're going to have to use product rule when we differentiate. But if we can break those apart into a sum, then that ends up being easier to differentiate. Or if we have a power of something, to differentiate that, we're going to have to use chain rule. But if we use our power law for logarithms and we bring that exponent down front, then we can use product rule instead, and it ends up being kind of a simpler idea, simpler for calculation, simpler for differentiation. And so that's what we're going to be using here. So when we're running into a product of things, and we're trying to differentiate a product of many different things, or if we've got exponents in them, then often this is going to be the case, is we're going to use logarithmic differentiation. So our bullets say it's a combination of using 30-1 rules. We're going to use implicit differentiation because we're going to differentiate both sides of this, used for more complex functions with many exponents, turns an equation from a series of products into a series of terms, which is easier to differentiate. So our first step is going to take the natural logarithm of both sides of our equation. We're going to use our log laws to break it apart and simplify it to differentiate it. And that's going to be our next step. So in this case, we have y is equal to x to the x. We don't really quite know what x to the x is going to look like. And so we end up with taking the natural logarithm of both sides. So ln y is equal to ln of x to the x. Now, I suppose you might know what our next step ends up being. It ends up being, let's use our power rule for logarithms. So x times ln x. So there's where the magic happens, is we've just broken this power down into a product of things. And now when we differentiate that, that's just going to use product rule instead of using chain rule. So we have the left side, ln y is 1 over y is what you get when you differentiate. It's implicit, so it's 1 over y times y prime is equal to derivative of x is just 1 ln x plus x stays the same, and the derivative of ln x is 1 over x. A ton of room for this question, so let's move up to here. We multiply both sides of this by y, so y prime is equal to y times ln x plus 1. And now we're going to replace y with what it's equal to. So if we look back at the original question, y was equal to x to the x. So x to the x times ln x plus 1. Number 2. So now we have y is equal to this whole big long product of these things. Could we use product rule and break it apart, and you'd have to do that twice? Sure we could, but it's going to be much simpler if we just take natural log to both sides. So ln y is equal to ln e to the x squared times x cubed times x squared plus 4 cubed. So we have the natural log of all of that, but it's a natural logarithm of a product, and so we can break that apart. So this ends up being natural log y is equal to ln e to the x squared plus ln of x cubed ln of x squared plus 4. Now we're going to use our power law for logarithms, and we're going to simplify that more. What that looks like, that x squared as an exponent, down front, x squared e plus 3 on x plus 3 ln x squared plus 4. Be careful, don't be tempted to think, okay, well, I'm bringing that 3 down front, I'm going to change this to 2 as an exponent. No, we're not differentiating that. We're using our laws of logarithms here. So that 3 comes down front, and that's it. All right, we are now ready to differentiate this, because we have now taken the logarithm, we've broken it apart into a sum of logarithms, and then we've taken each of those exponents down from within the logarithms, and so now we're ready to go. We differentiate the left side, and we get 1 over y times y prime. We differentiate x squared, and that's just 2x. Remember that ln e is just 1. So ln e just kind of evaporates away. So we have 2x on that first one. We have plus 3 times the derivative of ln x is 3 times 1 over x. And this is really the only one that ends up being formidable at all. We have 3 times the derivative of natural log is 1 over. Inside stays the same. And then multiply that by chain rule. Multiply that by the derivative of the inside. And the next step, y prime is going to be equal to, let's just tidy this up a little bit. So let's call this y, multiplying both sides by y. So we have 2x plus 3 over x plus 6x over x squared plus 4. Now, y is equal to e to the x squared times x cubed times x squared plus 4 all cubed. So that's just y. What's in the brackets here, we're going to get a common denominator. And so this ends up being 2x squared plus 4. It's 3 times x squared plus 4. 6x squared, just using a common denominator of x times x squared plus 4. Now, we want to tidy this up a little bit. the x squared stays here. Now, when we look at this closely, we have x cubed sitting out front here, and we have a factor of x in this square bracket here. So this factor of x and one of those factors from x cubed are going to divide out. Leaves us with x squared sitting out front. And similarly, we have x squared plus 4. We have 3 factors of it sitting up front on the left. We have 1 factor in the denominator, so let's divide that out. Clean this up. So we have e to the x squared times x squared plus 4 squared. And now let's work on tidying up what's left in here. We have 2x to the 4 plus 8x squared plus 3x squared plus 12, 6x squared, and we're almost done. E to the x squared plus 4. So that's all this front matter. And then we have 2x 4. We combine our x squareds and we have 17 x squared plus 12. And that is it. So kind of a big schmoz of a question, but the differentiation part made much simpler by this logarithmic differentiation. Number 3. Normally this wouldn't be that bad with product rule, except for the fact that our exponent on sine x is cos x, and so we would have to chain rule that. So let's try this by logarithmic differentiation. So we are going to first ln y is equal to ln of x squared sine x cos x. Our derivatives apart, or sorry, our natural logarithms apart. I'm kind of going to do this 2 things in one step here. I'm going to also bring that exponent down front. So let's call this 2 ln x plus cos x ln of sine x. So I did 2 things in that step. I separated it into 2 logarithms in addition, and I brought that exponent down front. Now ready to differentiate. 1 over y times y prime on the left side. On the right side, we have 2 over x. That's our derivative there. And now we're going to have some product rule with some chain rule in it. Derivative of cos is negative sine x. Derivative of log is 1 over. Inside stays the same, so that's 1 over sine x times the derivative of sine x. Cos x. All right, so now to differentiate. Left side, we have 1 over y times y prime. When we implicitly differentiate that, our right side ends up being 2 times 1 over x. So let's just call it 2 over x. And then we have cos x times ln of sine x. So we have product rule in here. So let's go plus the derivative of cosine is negative sine x times ln sine x stays the same. We're going to add that to cos x times the derivative of ln sine x. So 1 over sine x stays the same when we chain rule it, times the derivative of sine cos x. Now y prime is equal to y times 2 over x minus sine x, natural log of sine x. Careful not to call that sine squared. That first one is a factor of sine x. The second one is your argument for natural log, so it's ln of sine x. So be careful. That is not sine squared. But in this next one, it is cos x times 1 over sine x times cos x is cos squared x over sine x. In our next step, let's replace y with what it is. It is x squared sine x to the cos x. And we're going to need to get a common denominator in here to tidy this up. We have a factor of x downstairs, and we have a factor of sine x. So let's call this 2 sine x minus x times sine squared x ln sine x plus x cos squared x. All of this being divided by x. So in our next step, we do have, again, so the fact that we're expressing this as one denominator, so that's now a factor of the whole denominator is x, and here we have x squared, so we can divide that out. Let's leave that sine x downstairs for a minute. We'll talk about that in a second here. Leaves me with x sine x to the cos x up front. And then in brackets here we have 2 sine x minus x sine squared x times ln of sine x plus x times cos squared x. All of this being divided by sine x. That's pretty much as far as we're going to go with that. Now, a couple of things. Just to remind you, this term in here, this sine squared x times natural log of sine x, make sure again that you don't combine those sine x's. The first two factors of sine x, that sine squared that we have out front of the logarithm, is multiplying by the logarithm of sine x. So that last one is your argument for log in there. And so make sure you don't combine that. And then the last thing that I just want to mention is the fact that we have sine x to the cos x here. The fact that we have this factor of sine x to the cos x, and downstairs we have sine x to the 1. If we wanted to deal with that, think about what would happen if the numerator was sine x, not to the cos x, but to the 4, sine x to the 1. Well, that would divide out with one of those, and we would be left with sine cubed x upstairs, right? So we kind of do have this case where we could subtract 1 from your exponent. We do have that where you could subtract 1 from your exponent. What it would look like in our next step is it would probably look like this. going to be equal to x times sine x to the cos x minus 1 as its exponent. So we could do that just to tidy up that denominator if you wanted to. I kind of think either way, because that exponent is cosine x instead of just numerical or polynomial, I'd probably leave it as we had in the step before, but you could see it either way. So there we are. Last one. Y squared is equal to square root of x plus 1 over x minus 1. So when we log both sides, this is ln y squared equals ln of x plus 1 over x minus 1 all to the half, right? So this becomes 2 ln y on the left side. The right side ends up being 1/2. And now we have ln x minus 1. We can break that apart. 2 ln y is 1/2. And we have ln x plus 1 minus 1/2 ln x minus 1. If you wanted to that 1/2 common factored out front, square bracket that would be okay too. But this is now ready for differentiation. We end up with 2 over y is y prime is equal to 1/2 times 1 over x plus 1. Here's your derivative of natural log, multiplied by the derivative of the inside, which is just 1. So a lot of this is going to play nicely. 1/2 times 1 over x minus 1, when we differentiate that, times 1. So we end up with y prime is equal to y over 2, a half. I'm going to common factor that half out now. Then I'm going to get a common denominator. X minus 1, x plus 1, over x plus 1 times x minus 1, more commonly known as x squared minus 1. And we're almost done. This is cleaning up quite nicely. Y prime is equal to y times a quarter. I'm going to deal with y in just a second here. Y times a quarter. We have in the brackets, we have x minus x. We have -1 minus another 1, so -2 in the numerator over x squared minus 1. Now, when we go to substitute y back in here, let's look back at the beginning. This was y squared, not just y. So y really is equal to, if I square root both sides, this is plus or minus. This is now 4th root, right? When we square root both sides, so this is, it was x plus 1 over x minus 1 to the half. And then when I square root both sides, this is what we have. So it is the 4th root of x plus 1, x minus 1. So let's just write it as equal to, and then let's multiply it by -1 over x bracket x squared minus 1, just simplifying the 2 over 4. And that is it. So as always, any questions, please let me know. Email me and we can go over any of that. Thanks so much.